Hello, my name is Oskar Wallmark and I work as an associate professor at the Department of Electrical Energy Conversion here at KTH. In this presentation I will use basic tools from electrical engineering to motivate why our group carry out research on modular integrated electric drives for automotive applications. I'd like to start and have a look at the coming Volvo XC90 plug-in hybrid, where the driveline is shown here in this picture. This vehicle is equipped with an internal combustion engine here in the front, a battery located here in the middle of the vehicle, and an electric rear axle drive corresponding of an electric machine and associated converter or power electronic converter. It is obvious that if we can integrate the electric machine and the corresponding power electronic converter into a single unit, there are a lot of potential advantages. One is packaging advantages, the fact that we can squeeze in two components into a single unit. We can also reduce cabling costs, which can be quite substantial in a vehicle application. Then there are potentials for reduction in weight and in terms of EMI. As you saw, the electric machine and the power electronic converter is not integrated in a single unit, and I will try to motivate why that is so today and why it might not be so tomorrow. And I will start this discussion focusing on the most important component in the driveline of an electric vehicle, namely the battery. The photograph on the left-hand side here shows a lithium polymer battery subjected to impedance spectroscopy here at KTH. To the right-hand side, we have a very simple electrical circuit that we can use to model the dynamic behavior of this lithium cell. Here, on the left-hand side, we have admittance data obtained from the impedance spectroscopy you saw in the previous slide. It's obtained from measurements from a heavy-duty or heavy hybrid electric vehicle lithium-ion cell. To the right-hand side, we have similar data obtained for a non-heavy hybrid electric vehicle cell. And we can see the dotted lines corresponds to data obtained for different states of charge. The red lines are fitted data, where I have fitted the data corresponding to the simple electrical circuit we saw in the previous slide. Since it's difficult to fit the data to include the higher frequencies and the low frequencies, I have limited my fit to fit only data above 10 Hertz. These are the resulting model parameters that I get. The one on the top corresponds to the heavy hybrid electric vehicle cell, and the one on the bottom corresponds to the non-heavy cell, non-heavy hybrid electric vehicle cell. That's a lithium-ion cell. In order to operate in a vehicle, I need more than one cell. This figure shows the bus voltage for different vehicles out on the market today. And on the y-axis, we have the rated figures on the electric drivetrain, power figures. And of course, as the power goes up, so goes the DC voltage. I will select 400 volts. 400 volts. Each cell is rated at has an open circuit voltage of around 3.7 volt. That means that I need approximately 108 cells connected in series. I assume 2 parallel stacks to provide a sufficient energy content to propel a smaller electric vehicle. Now I have a model for my battery. To the battery there's a cable, a battery cable, say 5 meters of coaxial cable. The coaxial cable that I'm considering here has an inner conductor diameter of 7.1 millimeters. That means that it can handle, at 3 amps per square millimeter, it can handle 120 amps, which corresponds to 48 kilowatts at 400 volts. I can use these simple analytical formulas for obtaining cable capacitance and cable inductance for this specific cable. And here we see corresponding model fits and measurements for this specific cable. And we can see that the complex resonant frequencies that are characteristic of this battery cable, they occur at very, very high frequencies. And the red simplified model that we consider here is sufficient for the low frequency, the relatively low frequencies that we are considering here. Now I have a battery pack, I have a battery cable. To that I connect my electric drive. It consists of an electric machine, 3-phase electric machine of permanent magnet synchronous type, and a 3-phase power electronic converter, marked in red here, and the associated DC-link capacitor. The transistors in the converter today are mainly made of, consists of silicon IGBT switches. They can easily handle 400 volts and above, but they are limited in switching frequency to, say, 10 to 30 kilohertz. Due to the high voltage and the energy content that is required here, we will see the reason why later, aluminium electrolytic capacitors are most commonly used. They are the capacitors of highest energy density. They have an energy density of around 1 joule per cubic centimeter. The permanent magnet synchronous machine I'm considering in this example is a 4-pole 50 kilowatt machine. It can be characterized by these 4 parameters: the D and Q axis inductance, LD and LQ, the permanent magnet flux linkage, and the stator resistance. If this machine operates at 49 kilowatts, 6,000 RPM and 77 Newton meters, the phase current is around 150 amperes RMS and the power factor around 0.89. One of the main functions of the DC-link capacitor is to limit the battery current ripple within acceptable levels. The converter input current, I-conv, can be expressed as a sum of the 3-phase currents multiplied with switching functions SA, SB and SC. Here these switching functions are equal to 1 if the upper transistor is turned on, or equal to 0 if the corresponding lower transistor is turned on. Since multiplication in the time domain corresponds to convolution in the frequency domain, we can express the converter current in the frequency domain as this. The corresponding battery current is then obtained multiplying with the corresponding transfer function for this LC filter built up by the DC-link capacitor and the inductance of the battery pack and cable combination. I need some metric to characterize my battery current ripple. I've defined this peak-to-peak current ripple metric, summing all harmonics, the magnitude of all harmonics 2 times to correspond to peak-to-peak, and divided with the DC value. This figure shows the resulting current ripple using the current ripple metric that I introduced as a function of different DC link capacitance and different total inductances on the DC side, from 5 microhenry, which more corresponds to the small lithium-ion cell for a standard hybrid electric vehicle, up to around 20 microhenry, which corresponded to the prismatic cell for a heavy hybrid electric vehicle. From this figure, since I assume silicon IGBTs, I have used 10 kHz switching frequency, assuming naturally sampled asymmetric PWM. And we can see here that if we want to limit the battery current within around 10%, we need around or less than 1 millifarad. The figure below, the table below, shows three vehicles out in the market today, their corresponding DC bus voltage and capacitance. And we can see that we are in the range of 1 millifarad in the market today. I said previously that the energy density of aluminium electrolytic capacitors are around 1 joule per cubic centimeter. The practical energy density for a complete capacitor pack is substantially lower. Here we have values from 0.12 joule per cubic centimeter up to 0.27 joule per cubic centimeter. If I assume an energy density of the capacitor pack to be 0.27 joule per cubic centimeters, and if I need 1 millifarad, at 600 volts, 10 kilohertz, 1 millifarad, that means approximately a volume requirement corresponding to 2 soda cans. And these capacitors of electrolytic type, they are large as seen due to the high voltage. This substantially reduces the power density of the converter. They cannot operate above, say, 110 degrees, and they are limited in lifetime due to a wear out of the electrolyte due to evaporation. They represent approximately 5 to 7% of the total converter cost at 50 kilowatt. All these reasons above, they aggravate the integration of an electric machine and the inverter. The capacitor volume requirement is large. It's difficult to fit the electric machine and the corresponding power electronic converter into a single unit for this reason. Let's see what will happen tomorrow then. The following figure shows the specific on resistance, one of the important figure of merits for different semiconductor materials, as function of breakdown voltage for different semiconductors. The solid lines corresponds to derived theoretical limits. Blue is for silicon, green is for 4H silicon carbide, red is for gallium nitride, and the black is a limit obtained for silicon IGBTs. The boxes here corresponds to measurements on available switches, available components today. And if we look in the high voltage range, say 400 volts and above, we can see that both gallium nitride and silicon carbide based components, they promise significant improvements compared to silicon based IGBTs. If we go down to the lower voltage range, say 100 volts and lower, we can see that gallium nitride promises potential future improvements over today's silicon-based switches. Modularity for integration. The left figure here shows the conventional three-phase converter equipped with silicon IGBTs or silicon carbide or gallium nitride switches perhaps. In the middle converter, I've sliced the motor into 4 pieces and divided the converter into 4 pieces, each powering a small 3-phase machine. In the figure in the middle, these 4 sub-modules are connected in parallel to the battery, i.e. they all have to sustain the high voltage. And the figure to the right, there they are connected in series, meaning that they only have to sustain part of the battery voltage. Both the middle converter topology and the one to the right-hand side are modular in nature. The middle one has to sustain high voltage, so we can foresee that it will have silicon carbide or gallium nitride switches, whereas the one to the right will either use existing silicon-based switches or tomorrow gallium nitride-based switches. I will focus on the converter to the right-hand side where the sub-modules are connected in series. The modularity, namely, it allows for one more degree of freedom. Namely, we can cancel harmonics, reducing the battery current ripple by phase shifting the carrier of the modulator in each sub-module properly. This is called interleaving. And in the figure here, we have this converter comprising of 4 series connected sub-modules and the resulting battery current ripple as a function of the required capacitance. And without interleaving, we get the red line above, and if we interleave the carriers properly, we get the red line below. And we can see that we can, for the same capacitance, we can reduce the battery current ripple substantially if we carry out this interleaving properly. And this is a property that we cannot do on a conventional 2-level 3-phase converter. This degree of freedom is not available. This figure provides a comparison of the required capacitance volume. A, to the left-hand side, is today's state-of-the-art 600 volt, 10 kilohertz, 1 millifarad electrolytic type capacitors, i.e. we end up, as shown previously, with around 2 cans of capacitor volume. B is the requirement if we go up in switching frequency to 100 kilohertz, still at 600 volts level. We then need 25 microfarads for the same battery current ripple. And we can then go, the capacitance requirements in terms of capacitance is reduced significantly. We can then avoid using electrolytics. I have assumed a polyester type capacitor with an assumed energy density of 10 times lower than aluminium electrolytics. C is 150 volts and 100 microfarads per converter submodule. I consider the series connected 4 submodule converter with polyester type capacitor, and you can see the volume for case B and case C is the same. Case D is the case where I do this, where I phase shift the carriers correctly to reduce the battery current ripple even further. That lowers my capacitance requirement down to around 20 microfarads, 150 volts and 100 kilohertz switching. So both case B, case C and case D represents future technologies, and that we will see in the market, I think, in the relatively near future. Modular converters, they have these advantages that they have reduced capacitance requirements due to the high switching frequency and the fact that we could phase shift, interleave the carriers. I haven't talked about it, but of course, due to the modular nature, we have an inherent fault tolerance. We could design the converter so that it can still operate if one or more converter submodules fails. The challenge is to obtain a solution that is really competitive is to be able to carry out a design of a modular converter and a corresponding electric machine at the same time. In this presentation, I have not discussed the fact that series connected capacitors require active stabilization. We need an additional controller in this modular system, but this can be solved. And of course, we also need to investigate how should we handle faults in the best possible way. At my department, there are 4 PhD students involved in looking at aspects of modular converters for automotive applications. Le Bingjing focuses on converter topologies, modulation and control, whereas Morskan Nikoe Hanefors looks at converter design and control. Rudi Suarez, he looks at what are the impacts of battery current ripple on the battery. And finally, Hui Chang is working on electric machine design for these modular machines. The seniors involved are Mats Lexell, Staffan Norga and me. And you are very welcome to contact me or anyone else in the group. Thank you for your attention.